Mike Gamble. I'd like to comment on that. That's exactly what I'm doing.
Oh, yes. Show us. You have
Or tell us.
Do you have it right with you?
I have a demo model.
Oh, I should also ask, Douglas, was that everything?
I don't know how
or?
well you can see it on your box there, but there's 2 gyros in there.
Yes, thanks. I'll defer my other comments till after this.
Okay, thank you, sir.
So what does that do?
That does linear propulsion with 2 reciprocating gyros.
Okay, what kind of results have you seen?
I demoed that for Tom Valone at the COFE conference, and it does make propulsion.
Wow.
On what order of magnitude, and what is your test setup? Like, have you floated it in a bath of water?
No, just on a flat table.
And it loses weight, or is it moving along the table?
Moves along the table.
Okay, you should try it again. Just put it inside of a raft in a pool when the water is perfectly steady, and try it like that. That is the that's the best way to test something like that, because when you're dealing with lots of shaking parts, it's possible to for it to inch along, just like some some robots use that process of like shaking, because it all depends on the mount.
It's pulsed.
Yeah, and I think Tom Valone is actually with us today.
Yeah.
So.
He's familiar with it. He's got the videos.
You can go to www.futureenergy.org and get the link to Mike Gamble's video presentation at COFE 12, which was back in August. We were happy to give away the conference for free to everyone, and not too many people attended, but it was almost 300. I think we had a lot more than we would have in person if we were in Albuquerque. But suffice it to say that a few years ago, Mike predicted he could do it, and this year he did it. So I could actually share the screen and show you the video. This thing is so robust, it goes right across the flat table. This is not just inching along like all the other inertial propulsion attempts in the past history of this science.
If you're able to, that'd be wonderful. And welcome, Tom. Thank you for joining us.
Sure, you're welcome.
Tim, you're going to have to allow him to share the screen. It's on your controls.
Oh, okay. I'm sorry about that. Let me see. Let me see.
Dig up his video first on my computer, and then
but my concern with such an experiment would be that depending on the mounting pods and how it's shaping, how it's attached to the table, you could have a linear motion just from the vibrations alone. So putting it inside a bathtub or a large body of water and sitting it on a boat is really the gold standard for this type of test.
Oh, the pendulum test is also the gold standard. The pendulum test with it showing that it has a constant displacement to one side of the gravitational attraction would really be the gold standard. It shows a constant acceleration.
Pendulum doesn't work as far as pulsing. It only works if you have a steady state. If you have it pulsing, it'll start swinging.
Well, actually, Roy Thornton proved it in 0 point energy raised to zero. What was it? Free energy raised to 0 point. It's a video online, and you can actually see the pendulum staying to one side of the normal. So in the 1990s.
I'm just very concerned with how it's attached to the table.
Yeah. Let me see if we got the video from Mike Gamble, and we can show all of you.
Yeah, and you should be able to share, Tom, but let me know if it won't let you.
Right. Okay.
I like your Zoom background. It looks like a little German village.
Thanks.
Okay, I'm going to mute myself until you guys get that going.
Okay. Yeah, it's in the COFE 12 speaker videos, and what I should do is probably start the video and then basically fast forward it to the part where the demo is. Oh, wait a minute, I got the video separately. All right. Oh, you guys are gonna be happy about this. Okay, share screen. Host disabled.
We've got a little ringing going on from somebody. Somebody's mic should be muted because we've got some.
Yeah, let me mute David. Oh,
And
okay.
you have to allow me to share my screen, otherwise I can't share the screen.
Okay.
Okay, I'm going to pause it. Start at the beginning. It's just a 20-second demo,
Okay.
and I think we'll need to. When I click on share screen, it doesn't allow me to.
So I have, let me see, how many participants can share at one time? One participant can share at a time,
I'm
all
okay.
participants. Okay.
I got it. Okay, here we go. You guys should be looking at the screen now with this plastic thing with holes in it. Okay, there you go.
We don't see your screen yet.
You know?
No.
Oh, sorry. Okay, I can fix that. I think I have to press the word share.
Yeah,
And
share
that's probably-
screen.
That's probably a key to sharing screen. There we go.
There
Okay,
we
it's
go.
coming on now.
Okay.
We got it.
Yay. Okay, here we go. Full screen. And he's just holding the wires gingerly right above it. But this is the first trial run of the improved low mass version. And then we're trying to go for bigger gyros. Whenever Mike's ready, we'll order them. Instant replay. And this has been theoretically predicted. The first round, he actually measured it, the force of 0.4 pounds of thrust, and he predicted it theoretically as well. So that's a journal article in the making.
Okay, that's exactly what I'm talking about. Yeah, I like the rollers that you have over there. That's probably a pretty accurate prediction. I would like to try it though in water.
Oh, sure.
Yeah, we could set that up. That doesn't look very difficult to do. Just get two motors. It's actually the exact same kind of gyroscope that I have over here.
Yeah, processing gyros.
I would like to ask, is the motion of those two gyroscopes simply rotational, as in they would be rotating fairly centered to some axes, and they're simply having a different speed in one direction versus the other, or how is this force being generated? Can we clarify here?
Mike's got the whole thing. In fact, it's in part of a slideshow as well. And the whole presentation, 45-minute presentation's online. And I can probably give you a link to it.
It is difference in the speed. It goes fast in one direction, slow in the other, and the gyros are rotating at 16,000 constant.
Okay, so that would make sense from the relativistic perspective too, in terms of the difference in the acceleration velocity based on the fact that it already has some stored angular momentum in each gyroscope.
Will it work on a pendulum?
It will swing.
Like constant force?
It's not constant, it's pulsed.
Oh. I've done a lot of experimenting with these kinds of systems, not necessarily with gyros, but with pendulum type machines.
Yeah. If it supplies DC, then a pendulum will work real good, but if it's pulsed, it doesn't work very good at all.
It doesn't matter as long as it moves your spacecraft forward, though, really.
That's the whole thing, is will it work?
It's the difference between AC and DC voltage. They both do the job, but one comes in spurts.
I guess the better question would be, Mike, will this device produce a force in space?
Yes, that already does that.
He worked for
Boeing's
Boeing.
got them on their equipment.
That was the start of our interest in getting him to work on the civilian version.
I used to work for Boeing, and they have on all their spacecraft, and well, not only Boeing, but all the aerospace, they have 4 big gyros, and all your geosync satellites have them on there for that very reason. You don't have to have, you don't have.
There's 4 years of presentations on this topic.
Oh, wow. Yeah, that's fascinating. That's fascinating. I always thought the gyros on satellites were simply for orientation control, not necessarily for motion control or
They
any
do
kind of
both.
velocity.
They do
Yeah,
both.
Great.
If you spin the gyros opposite directions, you get torque. If you spin them in the same direction, you get linear.
Well, this is the highlights of the presentation. It's all
Well,
online.
thank you for sharing all this, Tom. This is
Well, you
wonderful.
can see the whole video is online, futureenergy.org, and you can see the link to it. It's all on YouTube, actually. 8 hours of the presentation, 2 days in a row. So,
Is there any momentum transferred from the spinning of the gyro to the forward motion, or
It's
does
Yeah.
the gyro
it's a change in
Yeah.
mass. The gyros add mass.
well, you've got the inertial moment of inertia to deal with. And he's got a master equation here too for the actual net force, but he deals with every moment of inertia first. I mean, Mike is meticulous.
And as he mentioned, the gyros are kept at a constant rotational speed, so they're not slowing down and transferring any of their energy in that way.
Little
Right.
bit, but not much. It's fairly constant.
And this is probably one of the best equations, right, Mike? Force,
Yeah.
peak force, and you've got the mass, the total mass and the radius, and then T is the time in seconds for the oscillation. And it's 0.48 pounds. You went from 0.4 to 0.48, right?
Yep.
Improvement. So you got a half a pound of force to really propel things along. But this is theoretical, and then you measured the force and actually found it matched.
Yeah, the numbers are pretty good. And you can see on the chart there's a lot of background vibration.
Yeah, and that's what we're trying to reduce now. Acceleration versus direct.
I have a question about the motors that are running this thing. So I take it there must be some motors that are spinning the gyros.
Yes, there's
And
one
then-
motor on each one.
And then there's some other type of motor or some electromotive thing or solenoid thing that's jerking them back and forth.
Yeah.
How do you reciprocate them?
There's a servo. Tom, can you put the picture back up of the side view
Okay, that's
of the carriage?
yeah. That's one side view.
No, the real picture.
The
He
real
wants to see the servos.
okay.
Yeah.
Yeah, right there.
Nothing.
Okay, under the picture on the left where it says left side, you see the gyro up in the air with the black cylinder, which is the motor that spins the gyro. To the left is another little black square, which is the servo motor, which turns it. And these the two little blue boxes on the left-hand side are the servo motor controllers and power supplies. And the big blue box on the right is the data acquisition.
And I take it if you were not spinning the gyros, but only reciprocating them back and forth, nothing would happen?
It still generates a little bit of thrust, but not nearly as much. The numbers there, I did it both ways to answer that question.
Actually, here's an example, right, Mike?
Yeah.
Gyro's not.
Gyro's not running with 20-degree cycling, and
You got another.
it generates a little bit of thrust, and then it goes way up as soon as you turn the gyros on. Essentially, they add mass to the system.
And that's with it running. And you can see all the noise that
Yeah.
gyro creates.
Yeah, the background noise goes way up.
Acceleration. So this is just the first prototype, and we're working on smoothing everything out to make it a really robust system.
Yeah, there's the comparison right there. From 108, whoops, you had it there.
Back up. Got the one you want?
Yeah, yeah. Yeah,
Well, you're up to
The
290 now.
one circled in red, which is 300 millig's, is with the gyros not running, and it goes to 483 when you turn the gyros on. And they're adding mass in that one axis by the spinning.
I don't know if you call it mass, but
Well, inertia,
inertia.
one-dimensional mass.
Force. I think it was ME.
And Tom, it's okay to put all of this up online with our conference video, right?
Yeah, it's already online. It's been
Okay.
online since August.
Oh, I just wanted to get your permission to post this part of the video and all of that.
Yeah. Well, if you want the slideshow, like in PDF, for example, that's a low enough file size I can send you.
I think this guy is really good because the
Yeah, in the end, we got some modified gyros.
You think that is Jamie at all? So good.
Just a follow-up question on that, about the efficiency of the system. So if you were to, so it's exerting a certain force, and which you could presumably measure on a, on a force meter.
Well, I have an accelerometer on the front that I use to measure it.
What is the efficiency, let's say, of the, the energy you're putting into the servo motors versus the amount of
Well, the
of
big
traction it
waste
can
is
produce?
spinning the gyros.
Work being done.
To spin up the gyros requires lots of force. Once you get them going, then the only power you're expending is the servo motors, which are a little more efficient, but the big loss is spinning the gyros.
But if you had very efficient bearings on your gyros, there aren't some kind of coupling of angular momentum transfer that would slow your gyros down if they had very good bearings.
It has ceramic ball bearings on there. They're from Gyroscopes Incorporated over in England is where we get them. And they're built very well. I'm amazed they hadn't torn the bearings out because the thing turns at 16,000. And we've put quite a few hours on them.
Thank you.
So the idea is that this effect is being caused by a relativistic conservation of some kind of, I don't know, relativistic energy. And also, I would definitely like to see this experiment done in a water tank to make sure that there's no friction with those wheels on the table or any sort of effect there.
You can
present them. Go ahead. Sorry.
You can hold it in your hand, and there's vibration sideways, but there is no force. You can feel it. It's all in one direction.
I would like to present a simple water-free test because you probably don't want to stick that thing in water, and also it might rock back and forth in water, which could be an issue. I've seen a great video demonstration, and I don't know if it was real or not, but the way they demonstrated it was good. They took a bunch of ping pong balls, which are fairly rigid and fairly spherical, consistently sized, and laid them out on a table with enough spacing so that platform placed on top of, say, maybe 15 of them at once could easily move back and forth. It basically reduced the friction of the system. And then they placed the box that had a device very much like your own inside of it. And I say like your own only because we don't know what's inside the box, but it moved in the same type of way. And I think the ping pong balls and that rolling action of the device being placed on a board would help eliminate a lot of questions about friction because the torque ratio of the friction there would
there's even a better there's even a better way. Use air hockey table.
Yeah.
Put a flat plate on the bottom and use air hockey table.
Right.
Tom's been twisting my arm to do it.
I love that idea. It's a great idea, Tom.
You can't wait to buy one for him. You just got to say yes.
Craigslist, eBay, somewhere. It's got to be cheap and available.
That's right.
Well, you could go to any of these video game parlors that have a hockey table and just rent it for an hour. They're like 4 by 8 feet.
What do we have to do to convince you to do that?
Yeah, what do we have to do to convince you?
Buy me some more time. I'm working round the clock. My wife's off the machine, and so I'm back in my office. I just got moved in here today.
Wow, okay.
Matter of fact, I'm doing calculations on stuff right now while the conference is going on.
And the bigger gyros are going to be ordered when?
Yeah. I wish I could give you an answer on that. I'm trying to order the servos right now.
Okay.
The
Coco
bigger
se arrepiente,
servos.
puede nadar y Martín no puede nadar.
Well, whenever you're ready, Mike, we'll get
Yeah.
this to a bigger scale where it's
Well,
not
I'm working on it.
I hope so. 4 years working on this. Amazing.
You know, it looks like, let me see, David Alzafon just said that he wants to thank everyone for coming. He's been called away and he's looking forward to the next meeting. So
we want to thank David too. Thank you so much for coming on and sharing your knowledge and all of the time and research with us all.
Yes, David, if you watch this in replay, thank you very, very, very much for, you know, and I know that this has been a true inspiration for Jeremiah and Mark and Jeremy Reese. I mean, this is, yes, they have talked about your father's work a lot, a lot.
Thank you, David, very much.
Oh, yes. Thank you, David. Yeah, he's probably dealing with lots of stuff.
Yeah, and I think that, well, and he's fighting that cold too, so.
Maybe it's COVID. Who knows nowadays? Yeah, I'm very excited to try that experiment as well. I'll try it inside of a bathtub if I can find a big enough, you know, laminar water place to place it. But from what I was seeing in this last experiment, I do think it would work. Are they spinning in opposite directions or they're spinning in the same direction?
For linear force, the gyros have to spin in the same direction. If you spin them opposite, you get twist.
Okay, are they? I'm talking about in relation to the axis of motion. Are they spinning in the same direction? Because if they're facing each other 90 degrees, they would be spinning in opposite directions, but relative to the axis of motion, will be spinning in the same direction. So
correct. Correct.
So which one is it? Which one is it? Are they spinning both spinning like this, or is one spinning this way?
If they're wheels of a car, would the car go forward or would it spin?
Okay.
Here comes Mike. He's showing you.
Gyros back to back.
A little bit higher, Mike. Move it up a little bit higher.
So they're spinning in opposite directions, but both.
We can't see it.
We can't hear him either.
Yeah.
You know, I think the words for something like this, you're actually probably looking for nautical terms, right? So you'd be saying, are they both spinning fore or aft?
Are they spinning like this? Mike, are they spinning like this together?
Yes.
Okay, so that's opposite direction.
Yes.
They're actually spinning on opposite direction based on their axis of motion.
Yeah.
Which is what I talked about earlier.
Yeah.
Okay.
And if you have them spinning alternately, then the thing just twists.
It'll just
back
spin around.
and forth
Yeah.
instead of moves.
Yeah, that makes sense. And you said that there is servos involved as well. What are the servos doing?
They're the ones that are torquing it. Supply the twist. It twists between 0 and 20 degrees. There's 20 degrees twist.
Up and down, or is it going, you know, left and right?
Yeah, left and right.
Left and right. Okay. Perfect.
It looks like swimming.
Like it swims.
Swimming breaststroke.
Yeah, there you go. Perfect.
Okay, very cool. Okay, so we'll try that. Have you tried more degrees than 20 or?
Oh yeah, I've run 20 is the optimum. In my presentation there for Tom, I do the whole optimizing game for speed, velocity, torque, and the whole thing.
Okay, I probably have enough equipment over here minus one gyroscope to set this up by tomorrow, but I'd have to take my remote control airplane apart to salvage some servos.
That's where they come from.
Yeah, that is where they come from. But like they mentioned earlier, you really can set that entire apparatus on a flotation device or on a board that you'd put on a air hockey table.
Yeah, well, that's the plan.
We actually had Steve Hampton do it for his presentation. We had 2 inertial propulsion presentations in the same day. So in fact, if you go to the URL I just posted, there's another one just for the entire conference, and that would probably be a double benefit. So here's the entire conference. I'll chat you that information too. That's the entire one, and then there's the one for Mike Gamble's. Steve Hampton actually did a bathtub demo at the very end of his. In fact, I could probably show you that too if you want.
Oh yeah, that would be amazing. That's what this conference is all about.
Okay. Yeah, he had a double rail that he attached his to. So okay, I've got it queued up right here. And
Mike, was your machine inspired at all by Sandy Kidd?
No, about 5 years ago, I presented a history of Boeing gyroscopes at Tom's conference there, and everybody says he wanted me to build one. So I built a model of it. The release from Boeing shows the big gyros. We had 4 big gyros that generated a couple 100 pounds of thrust. Boeing has been using these things since the 60s. Like I said, they're all on satellites for propulsion, and they call it station keeping because you don't have to store propellant, you just spin up the gyros.
So I got Steve Hampton's if you want to see it. I guess I'll turn the sound for it too. And Glenn Robertson from NASA helped him do the analysis. Okay, showing you the data first.
And maybe that's what we need to do the salsophone experiment.
Glenn Robertson's contact. Glenn was a consultant for this project. And Glenn ran his own conferences for years too.
Oh, do you think if you had 4 sets of gyroscopes, you'd be able to get a continuous motion?
Not necessarily. They're all pulsed, but it's like a car or internal combustion engine. They put a flywheel on the back side, but there's actual like 8 power pulses for a V8 or 4 or 1. And then the flywheel smooths it out. That flywheel is the inertia of the vehicle.
Right. It's part of the inertia. The car moving is also
Yes.
Inertia.
If you've seen my slides there, I calculate all the inertia for the individual parts.
But it definitely would smooth it out a bit, having 2 pulses, sort of like, higher frequency AC is more energy.
Yes.
Oh, okay.
Yep. The frequency of resonance increases.
It's like the Model T engine, right? 2-cylinder to 4-cylinder to 6 to 8. Then we got the V12.
There you go.
Come on, V12.
Now, is this Mike's also? And the reason I ask is when I do the write-up for this, I'm going to try and include as much as I can.
Yeah,
No, this is Steve Hampton.
Okay.
I give you
He's using rotating weights rather than gyroscopes.
Right.
You can see the weights on the bottom rotating.
And the bathtub
And he uses a solenoid for rectification.
Yeah. And the bathtub's coming up next. And by popular demand, the water boat bathtub. Here we go. Your wish is our command.
Wow.
I got two of them that work the same way, and I give credit to Roy Thornton, who started with a canoe. The canoe is the best one because it has no chance of benefiting from the backward stroke. And here's the pendulum test.
Audio is not coming through.
I don't see anything moving on the screen.
Right, not yet. He likes to talk.
Okay.
Yeah, I tried to get him to improve his video, but
Thank you so much for showing these. This is
Sure.
wonderful.
Put in a plug for the conference.
yeah, that's right.
Well, I will. I'll put in a plug and links, and we'll have all sorts of info there.
Yeah, futureenergy.org has the whole story and
You
the
see,
program and the papers
Yeah.
and slideshow.
you see it pulsing
Yeah, this is, I didn't think that was
when you do the pendulum test. It starts swinging because of the pulsing.
right. But Roy Thornton stayed on one side in that video, 300 races. This is not a very good demo, in my opinion. Okay, so that's it. That was the end of that presentation. Right, there's lots more.
Wonderful. Well, I guess I should ask what we're doing next. Tom, did you have some more that you wanted to share, or?
I got
It's-
tons to share. I mean, I could give it a whole 3-hour thing someday too, I thought.
Yeah, and
Priority.
again, David Alzafon had to leave. I sent him an apology email. I missed the chat window on that, but it looks like Wayne. Let me see. Well, Wayne had a question. Okay, Wayne.
Yeah, I actually had a question for Tom, which I've been wondering for years. This is awesome to be able to talk directly. But it has to do with this. Looks like my video was off.
Okay, I can hear you.
Yeah, it's in your book, Electrogravitics 2, and it was just about we were talking about the equation that Oleg Jeffimenko
Yeah.
described.
Actually, that's what we could do a whole seminar on if you want.
Okay.
I'm going to send an email and do Electrovitics 1 and 2, and we have number 3 and works. Now we're working on number 3. But,
Tom, if you'd be open to that, yeah, we'd love to have you back and do another session. And I know Jeffimenko is something that Paul Murat has talked to me about many times as well.
it's an amazing book. He talks about the first half, and it's two halves of the same book on gravity causation, and it's amazing that Murad's latched onto one half of it, and I found this electrokinetic equation, which, to tell a long story short, the word electrokinetic was very special, and the fact that Jeffimenko used it to describe this equation that basically produces a force from basically a very fast change in current, which is unusual. and yet it helps explain what Townsend Brown did with his tests on various things that were suspended. And then I found that Townsend Brown's first patent also used the electrokinetic word. And then I asked Jeff Amenko, did you know that that word's already been patented in a Townsend Brown patent? And he said, no, I never knew anything about Townsend Brown. So that's a parallel synchronicity and like minds at the same time. Very interesting.
Yeah.
So yeah, we'll think about it for another session just to devote to electrokinetics and electrogravitics.
Yeah, I think that's interesting. Well, and the thing that's exciting for me is, I mean, and I know you've been doing this with COFE for years, but one of the reasons that I wanted to moderate with this was just for the gravity modification, the anti-gravity inertial propulsion, for that community to be able to help educate and reach out, right? And so.
Okay. Well, I've got a research project tonight to finish, and I'm glad I was able to support Mike Gamble in his hand waving. So we look forward to bigger gyros next time. Bigger and better, onward and upward.
Well, thank you again, Tom.
Very welcome.
Yes, thank Michael for all that.